In section 2, we're going to take a look at performing a significance test for a mean. So a lot of what we do here is going to be similar to what we do with proportions, but a few things switched out to things that are specific for means instead. So with means, the first thing we have to decide is whether or not we're going to be performing a z-test or a t-test. So a z-test is for when we know the population standard deviation, which is our sigma. And a t-test is when we know the sample standard deviation, which is when they usually use either s sub x or just an x. We're going to usually perform a t-test. Okay. Most of our examples are going to be based off sample standard deviations, not population. So the first part of running a significance test for a mean is to state our hypotheses, our mean, and the level of significance we are looking at. So for the hypothesis for a mean, the null hypothesis, the mean is going to be equal to the mean of your claimed mean, okay? The alternative is when you have either greater than or less than or does not equal whatever your claimed mean is. Okay, so the alternative is the greater than, less than, does not equal. Okay, so then we are looking at our parameter, so whatever our mean equals, and then our level of significance is our alpha. Next, we check our conditions. So random, independent, and normal. So if we're performing an experiment, it will mention some type of random assignment. And if we're doing an SRS, that's when it's going to mention random sampling. So again, similar to what we've been doing, you look for the word random somewhere. Next, we're going to check independent. So that is our 10% rule. So we're going to check that our sample size is less than or equal to 10% of our population size, just like what we did with proportions. And then lastly, we have normal. So remember, for means, normal has one of or another condition you could check. So the first one is if your sample size is greater than or equal to 30, then you can assume that it's normal, right? If your sample size is less than that, you have to be told that the population or sample appears normal, or you graph it to make sure it appears approximately normal. If it doesn't, then we can't carry out a significance test. So when it comes to then calculating your test statistic, so just to kind of refresh what the generalized form is, it's your statistic minus your parameter over your standard deviation. So depending on whether or not we're running a z-test or a t-test, that changes whether or not we have a z-test statistic or a t-test statistic. So a z is your mean, your sample mean, minus your mu naught, all over your population standard deviation over the square root of n. T is your mean minus your mu naught over the sample standard deviation over the square root of n. They're very, very similar formulas. The only difference is whether it's a population or a sample standard deviation. Okay. Now, if you want to find the p-value, so the function we use in the calculator is also different because of this. So if you have a z-test statistic, you use normal CDF just like we did for proportions. If it's a t-test statistic, then we use something called t-CDF, which are both found with second vars. After we find our p-value, we still compare it to alpha. So from either normal CDF or t-CDF, So based on whether or not it's bigger or smaller than our significance level, we either reject the null or fail to reject our null. So then we do or do not have convincing evidence that the mean, and then it's always your context in words, based off whatever your alternative hypothesis is. Okay. And it is best to actually do an example of these to understand the process, just like with proportions. So the first example we're going to look at says a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. An SRS of 30 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8 hours. Do these data give convincing evidence that the new batteries last longer than average, use a significance level of 1%? So first thing we're going to do is write our null and alternative hypothesis. So, whoops, it's not a P anymore. It is the mu for mean is equal. So if we look, they are currently stating they currently last for 30 hours. So our mean equals 30. For our alternative hypothesis, we look for some type of greater than, less than, does not equal terminology. So they want to know if the new batteries last longer than average. So that tells me my alternative hypothesis is going to be greater than 30. Okay. So my x bar, my sample mean, is my 33.9, and my alpha, 1%, is 0.01. Okay. Now we are going to check our conditions. So first we're going to start with random, and it does mention an SRS. Okay. Then independent. So our sample size of 30 is less than or equal to 10% of all AAA batteries, which there's at least 300 of those, so we're also good there. And lastly, we're gonna check normal. So I'm always gonna start with my sample size. In this case, my sample size is greater than or equal to 30, so we're good. If my sample size hadn't been greater than or equal to 30, I would have then looked for words in the problem that indicated that it was normal. So now I'm actually gonna go and calculate my test statistic. So I have to decide whether or not my standard deviation is a sample or a population. And if I look back, it talks about how we did a sample of 30 batteries that had an average of 33.9 hours with a standard deviation of 9.8. So because that is based off a number of hours from our sample of 30, I know it's a sample standard deviation. So this tells me that I'm going to be doing a t-test statistic. So I'm going to do 33.9 minus 30 all over 9.8 over the square root of 30. Okay. I'm going to get a test statistic of 2.18. So now to find my p-value, I'm going to go to TCDF. Because my test statistic is positive and my alternative is greater than, my lower bound is going to be 2.18. My upper bound is going to be the 9s. And my degrees of freedom is 1 minus my sample size, which is 30, so my degrees of freedom of 29. So we're going to get a p-value of 0.0188. which I now need to compare to alpha, which was 0.01. And 0.0188 is greater than alpha. And when our p-value is greater than alpha, we fail to reject the null hypothesis. So what that tells me is there is not convincing evidence to show that the average battery life of the new AAA battery is greater than 30 hours. So remember, when we are performing significance tests or even confidence intervals with means, we have to remember our units for our problem when we're writing our sentence, because we're not dealing with percentages anymore, we're dealing with averages, and they are going to all have units associated with them. So one more example. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So something that we're also going to potentially see with means is given a list of data, and we have to calculate our x-bar and our sample standard deviation, which we have done in the past. So remember, we go into our stat function and we hit edit, and then we're going to put our data in a list. So 4.59, 5.04, 3.29, 5.23, 4.13, 5.5, 4.83, 4.4, 5.42, 6.38, 4.01, 4.66, 2.87, 5.73, and 5.55. Once you have all your values, you go back to stat and then calc, and then we want one variable stats. Okay. And then make sure it's drawing from list 1. We don't want a frequency list, and then we hit enter. So we want our x-bar and our sample standard deviation, so the SX. So x-bar is going to be 4.78, and our sample standard deviation is going to be 0.9386. So now, if we're looking at the problem, a dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Do we have convincing evidence at the alpha equals 0.05 significance level that aquatic life in this stream is at risk? So our null and alternative hypotheses. So our null hypothesis is based off the mean being 5 milligrams per liter. Our alternative is going to be less than, because it says that if it's below, then we have issues. Okay. I already wrote the sample mean up above, so I'm not going to rewrite it. Alpha is 0.05. Now we want to check our conditions. So random, independent, and normal. So for our randomness here, they did say that they chose random locations, so we're good there. Secondly, we have a sample size of 15. It has to be less than or equal to 10% of all locations, because we are looking at locations along the stream. So, and there's at least 150 locations along the stream. There's an infinite number. And then the last thing we have to do is check normal. Now, this is one of those special cases. So our sample size is 15. So our sample size isn't going to cut it. So what we want to look at instead is a graph of our data. And what you can use for the graph is kind of our 5-number summary. So our minimum, our quartile 1, our median, our quartile 3, and our max. Like if I were to create a box plot of my data, it's going to be symmetric. The min to the quartile 1 is a little under 2. The distance from quartile 1 to the median is about 2.5. Then the median to quartile 3 is a little under 1, and then our max. I mean, it's a pretty symmetric graph if I were to plot all of my data. So we're going to go ahead and say that it's approximately normal. And I'm just going to mention here that we used the graph. Okay, and again, when we're choosing what test statistic to use, we're going to use T because, again, we're going based off a sample. So our sample mean was 4.78 minus 5 all over our sample standard deviation, 0.9386 over the square root of 15. And we're going to end up with negative 0.91 as our test statistic. So now we're going to go to TCDF. So this time my lower bound is going to be my -9s. My upper bound is going to be my statistic. And then my degrees of freedom are going to be 14. And we're going to get a p-value of 0.189, which is greater than our alpha of 0.05. So again, we are going to fail to reject the null hypothesis. So we can say there is not convincing evidence that the DO level is below 5 milligrams per liter. Which means that aquatic life is not at risk. So let's also talk about type 1 and type 2 errors. So they work the same way with means as they do with proportions. If I reject when I should have failed to reject, it's a type 1 error, and if I fail to reject and I should have rejected, it's a type 2. So let's talk about a consequence of a type 1 error in this case and what it would be. So type 1 error is I reject the null hypothesis in favor of the alternative. So I'm saying that the dissolved oxygen level is below 5 milligrams. So I'm milligrams per liter. So we're saying that that would be determining that aquatic life is at risk when it isn't. So if we're assume because we are thinking it's at risk, then it's not. What we're going to do is use resources to fix it unnecessarily. So we're basically fixing a problem that doesn't exist. For a type 2 error, we say aquatic life is not at risk when it is. So that's when we failed to reject the null hypothesis when we should have. So we don't think there's a problem. So no one tries to save the aquatic life. And in this case, a type 2 error is the worst one to make, because then aquatic life is at risk and we do nothing to save it. And in this case, because we failed to reject, if we committed an error here, it was a type 2 error. But we may not have committed one at all. But if we did, it would have been a type 2, which is the worst of the 2 errors to make. Please let me know if you have any questions about significance tests for means or type 1 or type 2 errors in relation to those.